Now PN junction diode. This is P-type semiconductor. P-type semiconductor having majority carriers, holes. Holes are the majority carriers. So these circles, okay, the circles, they are now called as holes. They will be called as holes. The basic process how the holes are formed in the P-type semiconductor. Holes are formed because of the doping. Doping means addition of impurities in the semiconductor. In P-type semiconductor, we dope any trivalent atom like indium, gallium, and they are having 3 valence electron, and they comes in covalent bonding with the nearby 4 germanium atoms, and indium having less 1 electron. So indium also having gallium also having tendency to acquire configuration like noble gases. So gallium accepts the electron from the nearby germanium, nearby silicon, and when impurity atom accepts the electron, then it becomes the negative ion. Okay, and with 1 impurity atom, 1 hole is formed. So in the P-type semiconductor, the number of impurity atoms like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 are the impurity atom like gallium, and each impurity atom formed 1 hole, and 12 are the holes. Okay, these are the majority carriers. Of course, in the semiconductor, some electron hole pair are also generated by thermal energy. They are in addition. We're just talking about the carriers which are generated by doping. So this is N-type semiconductor. N-type semiconductor having majority carrier electrons. The dot will represent to the electron. Now how the electrons are formed? They are formed with the addition of impurity, pentavalent impurity in the semiconductor. When we add pentavalent impurity, they are having the 5 electrons, and this arsenic, antimony, they are pentavalent. They comes in the covalent bonding with the nearby 4 silicon atoms, but they are having extra 1 electron. So this type of impurity atom loses its electron. They don't need it. Okay, and when they lose the electron, they becomes the positive ion by losing electron. So whatever the number of impurity atoms, the same the number of the majority carriers which are electrons in the N type. Now what happens when P and N is mixed together? This portion is mixed now. So in the what happens, some hole they will diffuse in the N type, or you can say some electron diffuse in the P type. Electron tries to neutralizes the holes tries to neutralizes the electrons, but some hole gets neutralized, some electron gets neutralized. Of course, all the electron having tendency to neutralizes the hole. All the holes having a tendency to neutralize the electrons, but not possible. You know why not possible? Diffusion happens just for short while, then stops. And why further diffusion not possible? Because when hole and electron they neutralizes, the extra uncovered negative ion and uncovered positive ion, they create an electric field or barrier potential. So here on a p-type, on the n-type, the barrier potential develops positive. On the p-type, because of uncovered negative ion, barrier potential develops negative. So electron try to diffuse in the p, but this negative potential opposes. Okay, holes tries to diffuse in the n region, but this positive potential repels, opposes the hole diffusion. Okay, or you can say the hole they cannot diffuse in the n region to neutralize the electron. Why? Because of the potential of this uncovered negative ion. And similarly, these electron cannot diffuse in the p because uncovered positive ions, they opposes, uncovered positive ion opposes the electron to diffuse. So that's why the process of diffusion stops. Diffusion happens only for just a while. So fictitious potential or the barrier potential it develops. So this is the barrier potential. Now p-type semiconductor is now no longer neutral. It is now charged, some charged with negative. This p-type charged with negative, and this n-type is charged with positive. So this is potential barrier. Okay, so holes in the p-type, ions, now this is called depletion region. Now why it is called depletion? Because there is no majority carrier in this region. Majority carriers are depleted. There is no electron, no holes. That's why it is called depletion region. And thickness of the depletion region depends upon the doping. If the doping is very high, depletion region will be thin then. If the doping is light, the depletion region will be widened. So if it is, the thickness depends upon the doping, right? And it is, this part is also called the junction. So this is called junction because here electron and holes, they meet, they neutralizes each other, is a meeting place, and they neutralizes. So it is a junction also. This is p-n junction. Okay, and that this region is depletion region. Now we'll find how we make a circuit to obtain the forward characteristics. So this is p-n junction diode. This is now p-n junction diode. This is a potential divider arrangement. The potential is 10 volt. The whole potential is distributed over the resistance. Plus 5 to minus 5 mean 10. And P is directly connected to the plus 5. And N type is connected to a variable. Mean we can give any potential to N, okay, depending upon the position of the knob. So any potential can be given to N. P is at +5, okay. Whatever the potential given is read by the voltmeter, okay. The voltmeter is connected in parallel with the potential, with the voltage, and an ammeter is connected in series. So this is milliampere meter. It measures the current flowing, okay. So graph between forward voltage and forward current. So this is the graph. So just crossing the barrier, barrier across the PN junction. So this, just crossing the barrier, there is a sharp rise in current. So this exercise for you, just tell me what this voltage is called when there's a sharp rise in current, okay. This particular voltage is very important, and it is different for silicon and it's different for germanium, okay. What is the value, this value for germanium, and what is this value for silicon? This is a question for you. Now we're coming the reverse bias. PN junction, there's a potential divider arrangement. So this is PN junction diode. P is connected with directly negative. This is 10 volt. -5 to +5 is distributed. This P is connected directly to the negative, -5. And N is connected with a variable, can be given any potential. Whatever the potential given, reverse potential to Pn. Reverse mean P with the negative and N with positive. And whatever the potential given to the Pn is read by the voltmeter. Voltmeter is connected in parallel with the voltage. An ammeter in series. This ammeter is microampere meter because current flow is very, very small because it's a reverse biasing. Now we plot a graph between reverse biasing and reverse current. Reverse biasing along this side. This is a PN junction diode, okay, and there is a characteristics curve which we obtain experimentally. This VD, from where the current starts sharp, there is sharp rise in current, that is called VD voltage, and it is 0.7 volt for the silicon. And if it is a light emitting diode, this light emitting diode material is such that VD is quite large for light emitting diodes. But for the normal diode, if it is of silicon, this is 0.7. Now this equation exactly match with this curve. IS is the reverse saturation current. This value is 10 raised to power minus 12 ampere. This is very, very small. 10 raised to power minus 12 ampere. Eta is constant for silicon and as well as for the germanium. This is thermal parameters, thermal voltage. Now just multiplying the two. By multiplying the two, this is a constant for a given, maybe silicon, maybe germanium. The values lies in between 0.025 to 0.5. So now we left only one parameter, the forward voltage and the forward current. You go on substituting the value here, V, find the I. Theoretically at a given temperature, you find this value constant for a given temperature. Then substituting V, find I. Then verify whether experimental curve match with the theoretical curve or not. This is an exercise for you. Now this characteristics curve again. This voltage is 0.7 for silicon, 0.3 for the germanium. Reverse biasing, no current. Very small current in microampere. But at some voltage, breakdown takes place. Why breakdown? I'll explain to you why breakdown. And current again rises sharply. So this is called breakdown. Now what happened? Now we discuss why the breakdown. Now there are two types of breakdown. Okay, there are two types of breakdown. This is called Zener breakdown. This is called Avalanche breakdown. There are two breakdowns. This is Zener breakdown. Remember, this is Zener breakdown. It is at less voltage. Avalanche breakdown, it is at some high voltage. Now what is the reason of it? Now when it is the reverse biasing, P and N. Reverse biasing means P is connected with negative and N is connected with positive. If you go on increasing this reverse bias, means you are going along this side. What happens? Diffusion cannot take place. Some bond breaks. There is no diffusion, of course, due to majority carrier, no current due to majority. But some bond breaks in the depletion region because of the thermal energy. If the bond breaks, then there will be an electron and a hole pair. Okay, so what happened? The hole will accelerate towards this negative potential and electron will accelerate towards the positive potential. Like if this electron accelerates, this accelerates, and the way if the bond comes, okay, with the collision of the electron, again further bond, again electron and hole pair, a pair is generated. Now this electron is accelerating, this electron is also accelerating. Now in their way, again the bonds comes and again they collide with the other bonds and further bonds broken, and that means number of minority carriers starts increasing in an avalanche like a shower. So this is called the avalanche breakdown. With the collisions, the bonds are broken and process continues and a shower of minority carrier becomes available. But the crystal is damaged now. It is no longer to use then further. But if it is Zener, then no problem. Zener is of such a material, then you can use it for the next time. But Zener breakdown is at the less voltage. Zener is some, heavily doped. The avalanche which I am talking, a diode which breaks down by avalanche mechanism is usually a p-n junction diode with normal doping. But in case of the Zener diode is heavily doped. If it is a Zener diode, it is heavily doped. Heavily doped means depletion region will be very thin, not of this size, very thin. If the depletion region is very thin, electric field will be very strong, because electric field is potential divided by the distance, and distance is very small. This distance width, this width is very small, so electric field becomes very strong. Electric field is so strong that it pulls the electrons from the bonds itself. There's no electrons are not generated by the collisions, but the electric field, it pulls the electron from the bonds. Okay, so Zener diode, Zener has heavily NP regions leading to narrow depletion region and a very high electric field across the depletion region. Okay, again, I'm going to explain the avalanche breakdown. Avalanche breakdown usually occur for high value of reverse bias voltage, high value of reverse bias. The mechanism involves impact ionization, impact means collisions. The high reverse bias field favors the motion of minority carried across the junction. Okay, because of this potential they moves. Okay, and the current increases, which cause. Okay, now on the other hand, Zener breakdown involves the phenomena. This is a Zener is with the Zener diode. Zener breakdown involves the phenomena of quantum tunneling, which involves a high electric field causing to pull the electron hole pair from the covalent bonds. Okay, and causing them to cross the junction. So this happens for a particular voltage. Now I am coming the temperature coefficient. Lastly, again, the diode junction that breaks below 5 volts caused by the Zener effect, whereas the junction that experience breakdown above 5 are caused by avalanche. The Zener breakdown usually occur in heavily topped junctions, okay, which produces narrow region, depletion region. Avalanche breakdown occurs in light topped junction, which produce wide depletion layers like this one. With the increase in the junction temperature, now this is very important. What is the role of the temperature on Zener breakdown and avalanche breakdown? Okay. Now with the increase in junction temperature, Zener breakdown voltage is reduced. Okay, Zener breakdown voltage is reduced with temperature, while it is reverse in case of avalanche breakdown. While the avalanche breakdown voltage increases with the temperature. So Zener diode having a negative temperature coefficient, while avalanche diode has a positive temperature coefficient. This is a very important point. Okay, if T is more, then what happens? Zener breakdown voltage is reduced and avalanche voltage is increased. So this is what about the avalanche and Zener mechanisms. Okay. This is a PN junction diode. Okay, this is P and this is N. Okay, and when P-type semiconductor is given a positive potential with respect to the N, okay, when P is given a positive voltage with respect to N, the current flows to the PN junction, a heavy current flow, and we can say that it is a switch and which is closed now when the PN junction is forward biased. Forward biasing means current flows mean the closed circuit. And when P is made negative, okay, when P is given a negative voltage with respect to the N type, when P is given a negative voltage with respect to the N type, then no current flows. When no current flows in ideal condition, no current flow. So the PN junction can act as the open circuit, can act as an open switch. The switch is open. So PN junction is a switch, can be made on or off depending upon whether it is forward biased or it is the reverse biased, right? And diode mean PN junction is a diode. Di mean two, odd mean electrode. There are two electrode. One is anode and other is the cathode. So that's it is the diode. And diode is a switch, can be made on or off depending upon the biasing. Okay. Now looking here, this is the diode And if it is an ideal diode, when the current flows through it, no voltage potential develops across it. And if this is a 5 volt and resistance is 1 kilo ohm, by Ohm's law, the current becomes 5 milliampere. Okay, diode not offers any resistance to the current when it is forward biased. Okay, this is forward biased, and this is ideal diode. Ideal diode mean it is not having any resistance when forward biased. So only this is the resistor, this is the voltage, and current flows. Right here, the current, it acts as a closed switch. It is a closed switch and current is flowing through it. Now, if the diode is reverse biased means the voltage 5 volt, positive voltage is added to the N side with respect to the P, which is at ground. So that means reverse biasing. And it is an ideal diode, no current flows. Then this acts as a broken circuit, okay, off, the switch is off now. So no current flowing, that is the zero current. So this is how we understand PN junction is like a switch, can be made on or off depending upon whether it is at forward bias or it is at the reverse bias. Now looking here, now in the p-type, the circle they are holes, and these are the negative ions. Negative ions are always immobile, they cannot move. Similarly, here the dots are the electron and these are the positive ions. When the forward bias is given, P to positive with respect to N, so what happens? The holes and electrons, they diffuse. They are diffusing. Now when the reverse bias is given, minus to the P and plus to the N, okay, then current cannot flow because of here the potential barrier. How the barrier? Negative is here, positive is here. This is the barrier, this negative I because of the uncovered ions. Positive I because of the uncovered ion. So as the barrier stops, due to the barrier, holes cannot diffuse here, N side. And because of the barrier, electron cannot diffuse in the P. Now if you apply the potential exactly the same as that of the barrier, no current can flow, okay, because this outside potential favors the the barrier, and depletion region becomes widened. So this width increases, width of the depletion region increases with the reverse biasing. Now decreases with forward biasing, current flows. Increases with reverse biasing, no current flows. Okay, and open, no. Now close switch, current flows. Open, no current. Closed, very heavy current. Reverse bias